So, yeah, thank you all for being here. This is the final uh, series of talks for our quantum cosmology seminar series. And as advertised today, we have talks by some junior members of the community. We're very grateful for your interest and participation in this. I think we received almost 20 requests or proposals, and unfortunately, we couldn't feature everybody. But we tried in our tough decision making to select a broad range of topics, a broad range of viewpoints, a broad range of career stages, while sticking as close as possible to the core theme, which is quantum cosmology. But we were very impressed with the many really exciting proposals, and we hope to continue this in the future. And the seminar series will also continue in the spring, so stay tuned for that. But without further ado, I think our first speaker is Aurora, is that right?
So, yes, that's right. And I just sent a request to share.
Okay.
Sorry, you're not able to share already?
Oh, no, now I can. I had to send a request. Can you see my slides?
Yeah, we can see them. So first up, we have Aurora Ireland from Stanford telling us about a quantum to classical transition for inflationary perturbations. So please take it away.
Great. Thank you so much. In the interest of time, I'm just going to jump into things. I'll just note that this is some upcoming work. I'm not going to be able to do anything justice in 15 minutes, but hopefully I pique your interest enough to check out the paper when it comes out soon. And this is in collaboration with my wonderful collaborator, Vincent, who is at CNRS researcher in Paris. Okay, so if you believe inflation, and there's many good reasons to believe inflation, then the picture that we have for the origin of perturbations in structure in our universe looks a little bit like this. So during inflation, while the co-moving horizon is shrinking, the tiny quantum fluctuations of the vacuum get stretched to superhorizon scales relative to the size of the co-moving horizon. And when they are superhorizon, they're effectively frozen out. Eventually inflation ends, the co-moving horizon starts to grow again. And eventually these guys re-enter the horizon, becoming the, in source, the density perturbations that give us the seeds of structure in our universe today. And in principle, the statistics of these initial fluctuations should be imprinted on things like the CMB or, various large-scale structure maps or Lyman alpha, what have you. Okay, great. So the crux of this is that, in this story, the origin of these guys is quantum. They're fluctuations of the quantum vacuum. In practice, though, there are many contexts in which we treat, let's say, the curvature perturbation, co-moving curvature perturbation, which in principle is some operator. There are many contexts in which we treat this as just some appropriately defined classical stochastic random variable. I mean, obviously, we do this in things like stochastic inflation. But we also do this in a lot more mundane contexts, just like standard cosmological perturbation theory, when we're looking at these perturbations after horizon reentry. And I mean, yeah, very clearly after horizon entry, perturbations do appear classical, which, if you haven't stopped to ask yourself why, and actually this audience probably has, but if you haven't, maybe you should, because well, okay, so both why is this procedure valid, and also why more fundamentally it is that these perturbations appear classical. And the answer has to do with this quantum to classical transition that occurs while the perturbations are on these superhorizon scales. And there's a few different levels that you could understand this transition from, depending on whether you're viewing the universe as a closed system, an open system, which it fundamentally is, or if you want to go even more axiomatic. For the sake of this talk, I'm going to be focusing on this level 1, the level of a closed system, because this is the level at which this apparent contradiction or question that inspired this project came about. So at the level of a closed system, the story that we tell goes like this. It's the squeezing of the states, or equivalently in the Heisenberg picture, the fact that the decaying mode decays on superhorizon scales during, say, slow roll evolution, that allows us to replace what are fundamentally quantum expectation values with some, again, appropriately defined stochastic version. And to illustrate that a little bit more clearly, I have some math. So again, curly R here is some Fourier mode of my co-moving curvature perturbation. And I'm decomposing it into a piece that's proportional to creation and annihilation operators with momentum and minus momentum, because we're always producing these things in like momentum conserving pairs in like what's called a two-mode squeeze state. So these mode functions, if I assume again slow roll and bunch Davies vacuum conditions, look like this. And then pi here is going to be the conjugate momentum operator, which is defined with respect to r in this way. Where here this z squared is like the pump field that appears in the Mukhanov-Sasaki equation and describes the coupling between scalar perturbations in the background. And then this prime is derivative with respect to conformal time. So as I said, this is something that happens on superhorizon scale. So if I take the superhorizon limit of that mode function, then I get this natural decomposition of R into a growing mode piece and a decaying mode piece, where the growing mode piece, the leading order term, it's actually a bit of a misnomer, is a constant. And then there is some k to squared gradient correction and more gradient corrections. And then the leading order piece of the decaying mode goes like minus k eta cubed. And the fact that this also kind of naturally factorizes into real and imaginary parts suggests that a better way to decompose these things is to introduce these linear combinations of my creation and annihilation operators. And now in the superhorizon limit, obviously the constant part of my growing mode is going to be dominant here. And crucially, because the gradient correction to the growing mode actually falls off slower than the leading correction to the decaying mode, the conjugate momentum also to leading order, the red piece, the growing mode piece, is dominant. So you'll note that crucially the leading order pieces of these guys both go like the same operator. So what happens is in the superhorizon limit, you get this approximate commutation, and non-commuting parts are suppressed by this ratio of the growing mode to decaying mode, which becomes very, very large while these things are, out there for 60 e-folds or whatnot. And so, yeah, this is kind of the lore of why you are allowed to replace what should fundamentally be quantum expectation values with just, stochastic expectation values of some fields. Right. Okay. So that's the standard lore. But as you may know, there are many well-motivated scenarios where, the decaying mode begins to grow. In fact, I got into this from studying single field models that give you primordial black holes. And like in every single one of those models that is, amplifying small scale power, they're relying on a revival of this decaying mode. So it's ubiquitous, and you can ask the question, does this invalidate a stochastic description? Because if you follow the standard argument lore that I just gave you, it would seem yes. The answer is actually not necessarily. It turns out to be a lot more nuanced question whether or not a given observable can be reproduced with some stochastic description. And crucially, it kind of depends on both the observable and the state. So to make this a little bit more robust, we're going to introduce this object called the Wigner function, which I think it's probably more appreciated in like, say, quantum optics context, but we're going to introduce it in cosmology. It's formally defined as the Weyl transform of the density operator, and more intuitively, you can think of it as a quantum analog of the classical probability distribution, in the sense that I can use it to do things like this, to take like stochastic expectation values. And in terms of the Wigner function, a necessary but not sufficient condition for having this stochastic description is that this guy is everywhere positive and normalized to 1. So it can be used as a probability distribution. And negativity of the Wigner function is kind of seen as a hallmark of non-classicality. So the plan is very simple to state, very difficult to actually execute, but we're going to compute the Wigner function for the curvature perturbation in inflationary background undergoing some non-slow roll evolution. And we're going to use that as a diagnostic for if we can have a stochastic description. To do that, we need some heavy machinery. We're going to use the EFT of inflation. And then we're also going to use the separate universe approach inspired matching prescription. The reason why we need this first piece is, if we're working in linear theory, our Hamiltonian is always going to be quadratic and our Wigner function is always going to be Gaussian. In order to capture any non-Gaussian features, which is really what we're looking for here, we need some scheme to go beyond linear theory. And EFT of inflation offers one non-perturbative scheme. You could do other things, but this is the simplest way I found. I'm not going to go through it at all in the interest of time, but I'll just note that our central player here is going to be the Goldstone mode of broken time diffs. You can think of it as very closely related to the curvature perturbation in that it's also describing scalar perturbations around FLRW. And in the decoupling limit to leading order in epsilon1, this is the action for this Goldstone mode. So we've got some just kinetic piece, and then crucially, all the interactions are encoded in the chi dependence of the first Hubble flow parameter. Okay, so that action is our starting point. The other thing we're going to do is we're going to adopt the same trick that they use in the delta n formalism and the stochastic version, and that's on small scales, we're just going to use perturbation theory, and then on large scales, we're going to use the separate universe approach and just track the homogeneous mode. So we're going to initialize the state in perturbation theory at some matching time, T star. We're going to switch over to using our non-perturbative description. This is obviously only going to capture nonlinearities and whatnot at large scales, but these are, the relevant ones that are subject to parametric amplification during inflation. So this is a minimal thing to do. For my background, I'm going to pick constant roll. This reduces to slow roll and ultra slow roll and appropriate limits. The epsilon2 goes to 0 case is going to recover slow roll. Epsilon2 goes to -6 is going to be ultra slow roll. All right, I'm skipping over all of the details. If you are interested, I would love to talk more about this. Please contact me afterwards. But just to show you what we do, we have a homogeneous mode Lagrangian. We do a change of coordinates. We solve the Schrodinger equation with some ansatz. We set the initial conditions in perturbation theory. And then this is the wave function that we get for this, the homogeneous part of the Goldstone. And this part in red is where all the physics is. So we've got some, double exponential structure. And then the limit that epsilon2 goes to 0, you do recover just like a nice Gaussian for slow roll. And then this is how we're going to calculate the Wigner function. In the slow roll case, it's just a multivariate Gaussian, which is, exactly what you would expect, exactly what you find in linear theory. If you compute the covariance matrix and you take the determinant, you find that it's a quarter. So this is a minimum uncertainty state. And then if you look at what the contours of this Wigner function look like in phase space, you get these nice ellipses, and it's everywhere positive. The squeezing is controlled by the squeezing parameter, and the orientation is controlled by the squeezing angle. Just the standard story. In ultra slow roll, I'll spare you what the expression looks like, but this is what the Wigner function looks like when you actually evaluate it numerically. So this is for a benchmark point taken soon after the matching time and kind of near the limit of perturbativity. So you can see that the distribution is still pretty localized around the origin, but it's no longer obviously Gaussian. It's got these oscillations that are radiating out into one of the quadrants, and our ellipses have been kind of deformed into this L-shaped thing. If I go to a later time, it becomes more dramatically non-Gaussian. I still have my oscillations, but I have this like additional wavelet structure on top of that, which is quite interesting. And you can understand mathematically where this is coming from. Again, skimming all over the details. If you have questions, please contact me. In terms of something meaningful we can compute from this, we can compute what's called the Wigner negativity. So this is kind of like the simplest, dumbest thing you could do to quantify how negative this thing is. I'm just taking the absolute value of the Wigner function and integrating that over phase space, and then subtracting by 1 because this thing is normalized. And here is the e-folds that have happened since the matching time. And here is the negativity. And you can see that it's actually this really nice linear evolution law, which gives me great confidence in the numerics for this thing. And you can see that, crucially, it's increasing with time. And then you can take some lessons away from this. The first being that quantum effects can become important. And, we should be careful about just naively employing some stochastic description if we're going away from slow roll. Another lesson is that the squeezing picture is, actually insufficient to diagnose classicality. Actually, you know what? I'm just going to go through these one by one. So the first thing is that, yeah, since W is not positive, you can no longer interpret it as a true probability distribution. I should note that, just because it goes negative in some far off region on the tail of the distribution doesn't automatically rule out having some stochastic description. What really matters is like if you have some operator where that thing's support is in phase space, and so long as the support of that operator is coinciding with where the Wigner function is positive, you can still use it as a probability distribution and probably get the right answer. But you need to check kind of operator by operator, which ones are affected. We're working on that now. Another thing is squeezing is not tantamount to classicality. The lore that I gave you in the beginning was actually not quite right. And if you stop to think about it, it makes a lot of sense because a squeeze state is still like fundamentally a very quantum state, as people in quantum optics know very well. It's just that it appears classical under a certain class of coarse-grained observables. And the squeezing amplitude by itself, that's not something that's inherently meaningful. You can always get rid of it just by making a canonical transformation. And because of that, there's no reason it should really be tracking intrinsic properties of the state. You could contrast this with something like the Wigner negativity, which you can show is actually invariant. Another really interesting thing is if you follow that squeezing argument that I gave at the beginning, you would reason that classicality is something that happens when one like linear theory mode dominates over the other. And following that logic, you would think that ultra slow roll should be equally as classical as slow roll. Because during ultra slow roll, what you call the growing mode and what you call the decaying mode switch places, but you still have this hierarchy of the modes. But we're seeing that that's not the case, which is really interesting. This is also kind of surprising from the point of view of the.
Sorry,
Okay,
you're the 15 minutes, so just wrap up. Yeah.
Yeah, okay, I'll stop. I'll just say that it would be great if we could find some signature of the quantum origins of fluctuations in our universe. The usual counter argument is squeezing. Yeah, maybe that's not the case. I'll end there.
Okay, so yeah, I think I'm taking over from Brian as the host here. So maybe if there's one quick question we could squeeze that in. Should probably keep moving along. Okay, well maybe let's just thank Aurora one more time and we'll move along to